design control system. And then we have to check the chart controllability. Then we can specify our pole locations. And then we can adjust our steady state response. So this is the basic design procedure for a control system. Okay? So if okay, then let us start. So for example, if we have a water tank system, so we have the resistance of the outlet, and then the resistance between the tanks, the cross-sectional area, the height of the water level, this A1 and then H1, and then the inlet flow rate, so first of all, we set up the differential equation. We balance the inlet and outlet. So we have A1H1 equals the inlet, subtract the outlet. So we can rearrange the equation, and then we have and then for the other tank, for the second tank, the inlet is only from tank 1, and then the outlet. Then rearrange, we have so from the differential equations, we set up the state space equation. So we put the differentiations on the left-hand side, and then we construct the matrix. So we have the state space equation in the matrix form. Right? Then we plug in the numerical values. If we let simply, but just for example, okay, just for example. So if we have these numbers, then the matrix equation or the state space equation becomes minus 0.1 and then 0.1, 0.1 and minus 0.2. And then if the water level in tank 2 is of interest, then the output is okay. Right, any questions so far? We're interested in the water level tank 2, H2. So 0 times H1 is 0, 1 times H2 is H2. It is, for this problem, if we are interested in the water level tank 2, okay? Okay, our next step is to find the transfer function. First of all, we take Laplace transform. Then rearrange. Then we have the transfer function is the G equals C, and then Si minus A invert times B. Okay, now the matrix Si minus A equals then we proceed to calculate the inversion. So first of all, we find the minor matrix. So it is S plus 0.1 upon 2. And then we also find the cofactor matrix. And the adjoint matrix. which is the transpose of the cofactor. Okay, and then coincidentally, it is the same. Then we find the determinant of the matrix. So it is S plus 0.1, S plus 0.2, and then minus 0.01. So this is the determinant obtained for this matrix here, Si minus A. Determinant of Si minus A. Then the transfer function is G, and then our C matrix, and then the adjoint matrix, and then our B matrix, then totally divided by the determinant. So if we work it out carefully, then we have we take out the determinant, and then this part, it is 0, and then what left is the second row. Yeah. And then multiply with B. Then it becomes okay. And then from here, things getting a bit complicated. Okay, we factorize the denominator. So we complete the squares. So S equals and then divided by 2. And so very unfortunately, we do not have some nice magic numbers, but quite difficult numbers. So the transfer function, we do an approximation. Just do a simple approximation as plus 0.26. So we take 2 digits after decimal. Here we approximate 2 digit. Now we see that the transfer function has three terms. So the three terms, we call it G1 equals K. K is 0.1, that is the gain. Okay. And then we let G2 equals S plus 0.26. So we have a phase lag term. Okay. And then the break frequency is 0.26. The third term is the S plus 0.04. It is also a lag term, and then the break frequency equals 0.04. So for all the test frequencies, to construct the Bode plot, so we set the frequencies at 0.026 and then 2.6, then 0.004, and then 0.4. So here it is 10 times below break frequency. Here it is 10 times above the break frequency. So the magnitude of the term 1, the magnitudes of G1, okay, equals 0.1. So it is 20 log 10, 0.1. So it is minus 20 decibel. And then the important thing is that it is constant for all frequencies. And then the angle of G1, okay, it is the arctangent, the zero, the imaginary part over the real part. So it is 0 degree. Again, this is also for all frequencies. Okay with this? Okay, and then for the other term for G2, when the frequency is 0.026, okay, the magnitude is 0.004. 0.026 square plus 0.26 square. So it is approximately approximately 12. Okay, and then the angle is so it equals minus 6 degrees, so we approximate it to 0 degree. And then at omega equals 2.6, so the magnitude is minus 20 log 10. It is 2.6 square, 0.26 square. So it is approximately minus 8. And then theta is equals minus 84, and then we approximate it to minus 90 degree. Yeah. The negative is because it is on the denominator. Okay. Yeah. For
how are you finding sorry, go on.
continue your question.
Sorry, my question is, how are you finding what's under the root side?
Oh, what under the root is the so it is the real part. This is the imaginary part. Remember the magnitude of a complex number.
Yeah, the imaginary.
Come from here, omega.
Why is that imaginary?
We have S going to J omega and then goes to this omega. So originally it is S here. From S, and then we put it to J omega. So it is the imaginary part. No worries.
And so, oh, sorry, one more. And the negative side of the tan, that's also the
The negative arctangent is because this factor is on the denominator. So okay, and then for the other term, right? For this term, we test another two sets of frequencies. Is 0.004. Then the magnitude is plus 0.04 square. So it is approximately 28. Okay. And then for the angle, it is also, we approximate as 0. And then omega equals 0.4. Then the magnitude is so it's approximately 8, and then the angle, it is approximately 90. Okay, we have the magnitude and angle of the test frequencies. Okay, and then now proceed to draw the body part. And then first of all, we note the note in the log scale. 0.26 goes to minus 0.6, and then 0.04 goes to minus 1.4. Okay, on the right hand side, it is a log scale. So is that okay here? Up to here. Okay. Then we construct the frequency scale, the frequency axis, the omega. Okay. Yeah. Just log 10. Just log 10. Log 10 scale. And then we log that frequency range of interest, right? We test the frequency from 0.004 to 2.6. So we start with somewhere 1 and then 10. Okay, 1 and 10 covers 2.6. In fact, 1 is 10 to the power 0. 10 is 10 to the power 1. And then we roughly use the same scale as 10 minus 1. And then it's 10 minus 4. Okay, so it is 0.1 is minus 2 is 0.01. And then we still have another 10 minus 3 is 0.001. Okay? Then we look at the break frequency. Okay, 2.6. So it is 0.5, and then here, roughly, it is 2.6, and then it's 5, and then roughly, it is 0.26. And then we have 0.04 is minus 1.4. Okay, 0.04. And then it's 5, and here 0.004. Okay. So in log scale, here, the log scale. Log scale here, it is 0. From here to there, it is minus 0.6. From here it is 1. From here to there is minus 1.4, etc., etc. Then to here is minus 2.4. 0.4 should be here. 0.4. Minus 0.6 should be here. So this point is minus 2.4 up to here. 0.4, 0.6. From there, we construct our ball plot magnitude. Okay. So we set this as 0 decibel to set this line. And then this is minus 20. It's minus 40. Here, okay, it's 20, and then it's 40. Okay, we call that the first term. The first term, the magnitude is minus 20. Okay. So we have a minus 20 for all frequencies. Okay, this is G1. And then for the second term, when it is 0.026, we have 12. When it's 2.6, we have minus 8. So at 2.6, somewhere there. And then 0.26. So at 0.26 is 12. Okay. And no, not here. Then 0.26 is somewhere here. And then this is the break frequency. So all below that is a constant. And then at 2.6, it is minus 8, somewhere here. Okay, minus 8. So here it is 12. So an approximation will be like this. And then for the other term, for the this term, okay, we have 28 and 8. The break frequency is this one. And then 28 is somewhere here. So this is the break frequency. And below the break frequency is always a straight line. And then we also calculate 0.4. Okay. 0.4 is somewhere 4 is 1.4. So 0.4 is somewhere 28. Point 4 is somewhere here. Point 4 is greater than 0.26, so it is somewhere here, but not to scale by freehand drawing. Okay, so at point 4 the magnitude is 8. So we have 10, and then somewhere here. So it is 8 decibel. Then the overall response is, here it is 28, and then here is 12. So the overall magnitude at low frequency for example, it is 0.004. So it is 28 plus 12 plus minus 20. Okay, the 12 is for the M2. Okay, so it is for the magnitude 1, this is magnitude 2, this is magnitude 3. So it becomes 20. Yeah, somewhere. From there, we have one decreasing slope, and then this is continuous. So we have something like this, gradually decreasing. Okay, and then we have a more decreasing. And then especially at the high frequency here. Okay. And then the overall magnitude at high frequency. For example, it is 2.6. So it is 8 here, and then it is also approximately 8 here. So it is minus 20. It is minus 8 plus minus 8 plus minus 20. Okay, so it's minus 36. Minus 36 is somewhere here. Okay. So we have something. So it is the approximation. Approximate the magnitude. Okay. And then for the plots, remember to give the labels, right? Because in the freehand drawing, it is not to scale, right? And then for the frequency, for the angle. So if we set this, the omega, it is 0 degree, and then the minus 90 degree, and then minus 180 degree. And then we have the same frequency here, okay, 0.004, okay, 0.004. and then 0.04 somewhere here, and then 0.26, 0.04, 0.26, and then somewhere it is 2.6. So for the first one, okay, it is the maximum is minus 19 below that, and then the maximum phase change or the angle change is minus 80 degree, and the minimum is 0 degree. For the second and third terms, they are the same, but at different frequencies. Okay, at the break frequency, it is upon this 45. So this one is for 1 over s plus 0.26, and then this one is for 1s 1 over 0.04. And then overall, it is again, we multiply them together. We add them together. So the overall okay, we add the terms. So we have our bow plot. Okay. Okay. Okay, for gain and phase margin. So the magnitude is, in our example, and then the angle it is minus arctangent minus 1. This. So the frequency at which so it's just equate the okay, then set equation 1 equals 1. So in this case, we can find then solve for omega. Okay. So at this frequency, in this example, right, it is okay. In this example, then the angle is so it is minus 170, 127. and phase margin is 180 minus 1. And then we observe that since our phase change within the minus 180, then the gain margin is infinitive. Okay. Then we can find the bandwidth. It is the frequency at which the is 3 decibel below the zero frequency or low frequency. In this example, it is 20 minus 3 equals 17. So it is equal to 10, 17 over 20. So it is also 7.1. So it is also all in decibel. So then we convert it to natural number. From there, then we solve for the omega. So in this example, it is 0.0374 radian per second. For this case, solve for setting, okay, it is setting equation 1 equals 7.1. Equation 1 is the this one, the magnitude. We set the magnitude to this natural number 7.1. 7.1 corresponds to 17 decibel, which is 3 dB below the low frequency. Okay. Okay. So we are from transfer function. The transfer function is 0.26, 0.04, and then 0.1. So, and then we see that poles at minus 0.26 and minus 0.04. So we see that it is close to 0. Okay, making system likely to be unstable. Okay. Also the rise time is long, okay, because of small bandwidth. Okay, we saw that the bandwidth, it, we found that the bandwidth is very small, and then it's not desirable. Then what shall we do? Okay, then implement pole placement design. So the first question is is the system controllable? Okay, then we check the matrix. Check matrix. It is BRAB. Okay, this is for second order system. And then with our example, the numerical values, right? Then put in. So B and then AB equals 1 and 0, and then minus 0.1, 0.1, 0.1 minus 0.2. So if we do it carefully, we have this. And then the determinant is 1 times 0.1 minus 0 times 0.01. 0.1, it is not 0. So it means that BAB is invertible, and the feedback gain can be found. Okay, agree with this? That we just saw it last Friday. Yeah. Bandwidth, yeah. Minus 3 is the definition. Here. No, it is 3 decibel below the low frequency, because our low frequency response here it is 20. The overall system response is 20 here. So 20, and then we measure it 3 decibel down, it becomes 17. Okay. Okay, suppose require poles at -2 and then -3. Then the characteristic equation required is S plus T and then S plus 3. And then we'll let gain vector K. It contains two elements, K1, K2, because of two states. Because of two states. Then we have x dot equals a x plus b u, and then we put u equal minus kx, so it is a x minus b kx equals a minus b kx equals a f x. So this one is the feedback system. So we find the determinant, okay. We find the determinant of Si minus AF. So it is a bit calculation, then it becomes S squared plus 0.3 plus K1 S plus 0.2 K1 plus 0.1 K2 plus 0.01. And then we match terms. Match terms, we have 0.3 plus K1 equals 5. So this is the 5 that we want to match. Okay. So we have K1 equals 4.7. Then match term again. Match term, it is 0.2 K1 plus 0.1 K2 plus 0.01 equals 6. And then it gives us K2 equals 50.5. So now our system becomes this, in this way. So we have x dot and then x, and then we have the A matrix, and then we add together, and then the B, the gain matrix, and this part is the U, and then the output C of x, and then we get the Y. Okay, this is the open loop system so far. Okay, the open. And then we construct a feedback loop. Okay. And then we have a feedback. And then we adjust the reference. So this is for our feedback. To put poles at -2 and then -3. And then for the KR here, it is adjusted to match our steady state response. Okay, is that okay? See here. Okay, the final step, right? The final step is, you got it or not? This one. Okay. So now what we have, the state is ax plus b e, and then the kr minus kx. So it is so it is a minus bk of x plus br. br, okay. Okay, the last step is that we calculate the transfer function again, fun g again. So it must be okay. So it is because of pole placement. So we have a new transfer equation, and then the steady state response is response is 0.1 over 6. Okay, it's not equals 1. The response to t unit step. Then put the kr equals 6 over 0.1. So it is equals 60, right? So we'll respond to unity with a unit step input. Okay, that is almost all the design process, right, for a given system. So, okay, we go through the frequency response analysis, right, and then we also go through the state space design, right, so that the system will satisfy our required response. Okay, that's it for the example. Thank you.
Thanks for that revision. Question. I submitted my lab report late. I was just wondering if you got my email.
The lab report?
Saying that I submitted the one. I was just wondering if that was I submitted to Moodle. And I sent you a link to the lab report. Yeah, I just wanted to double check that.
So can we get you to log in as well if you use this?
Oh, right.
Yeah, yeah.
And then we will try to upload the text to it. In a week.
Okay, no worries. I just wanted to double check that now. We received that. Thank you.
Thank you. Thanks.
why is it changing values after when we did it was at I don't think so. I think it's when you're so close to infinity, when you mean like the like what do you mean? And that's where 20.
This is the one, right?
No, where does 20 mean? No. Okay, but I don't think that in my. Why are we doing it at this magnitude? Where does this or this frequency come? Okay, that's okay. So I don't believe.
Right, we have a question here. Is it a bit too loud? This should be better, but it's not. Okay. I hate hearing my own voice. I don't know how you manage it. Anyway, we have two systems with some similarities and some differences. So how different are these two transfer functions? G1 OS, G2 OS. So what is the relationship, or what is the difference between the two? Not sure? Don't know? Want me to do it? Yeah, oh, okay, oh, you are here. Oh, for a moment I thought you were hypnotized. Okay, so system one, if we sketch a free body diagram of this mass M, then you have Fi pulling the mass down, and you also have these two forces resisting the displacement of mass M downwards. So this would be Kx, and this would be Cx dot. The algebraic sum of all forces equals to inertia. So if the downwards is positive, then Fi minus Kx minus Cx dot equals to Mx double dot. Separating input terms and output terms, gives us the differential equation, or dynamic equation, or how we also call it, a mathematical model in the time domain of this system. So the transfer function, when you apply Laplace transform to the left-hand side, right-hand side, assuming zero initial conditions, you will get output over input, which is G1 OS, will be equal to 1 over 1 over ms squared plus cs plus k. Now this system, M, has a force Fi pushing from the top downwards. As a result, this spring is going to resist the motion of the mass m. So it is kx. The other end is 0. I didn't point out. So these 2 points are fixed. So it's not, in this case, it is kx, not kx minus y. So if this is y, y is 0 anyway. And the same here. This point is not moving, so y dot would be 0. So therefore, c x dot. On this side, so it is again kx because this point is not moving, so y would be 0. And also this damper is resisting the force acting downwards, so it is c x dot. Algebraic sum of all forces Fi minus kx minus cx dot equals to inertia mx double dot. G2 equals 1 over ms squared plus cs plus k. So these two are equal. So the conclusion is that it doesn't matter where you put your components. All you have to ask yourself, is this component, is this spring resisting the input or not? So these two springs are doing the same thing, resisting this input force. Okay. And we could play with this, combining these three components any way we want. If you want to put one spring, the spring on top and damper at the bottom, as long as the other end of the spring and the damper is fixed, we'll get the same transfer function. All that matters is these forces generated by spring and damper, in this case, resist the input force. So therefore, negative sign. Okay, any questions or comments? Now, some people emailed me asking if I could be, today, if I could be more specific about what will be in the exam. Stating the mid-semester test when I was very specific about one of the questions and said, well, did you see how good the marks were? You know, so I decided to modify that. So I'm going to go, quickly solve this problem, this exam question, but it's actually last year's exam question, not this year. So that's not exactly what those, well-meaning people wanted, but close enough. So I'll go through this problem. I posted it, I think yesterday. When was it? So I hope all of you have seen it. But here, just quickly, so we have an open loop transfer function. And yeah, we are going to do a few things with that open loop transfer function. So part A of this question, so Q1. Part A, what is the order of the system? Do we know what is the order of this system? I don't think I can hear a unique answer to this. So the order of the system is determined by the order of the transfer function, obviously. The order of the transfer function is determined by the order of the polynomial in the denominator, or the order of the characteristic polynomial, which is 3. Because this transfer function can be rewritten as k s plus 1, s cubed plus 2, s squared. Okay, so the order of the polynomial is 3, of the polynomial in the denominator, the order of the characteristic polynomial. So order is 3. What is the type of the system? Yeah, it's second order. I couldn't see the number of fingers here, sure. Okay. It is second. Why? Because the type is determined by the number of integrations contained in this transfer function. 1 over s means integration. So you have 1 over s squared. You have 2 integrations. Or the other definition of type is the number of poles that are equal to 0. So here we have 2 poles that are equal to 0 and 1 pole equal to -2. So it is type 2. Okay, so this is simply about knowing what the order is, what the type is. No particular calculation, therefore only 1 mark, half a mark for each of these answers. Part B, determine the steady state error of the closed loop system if the input is, and now we have 1, input R, ROS, okay, is a step function of magnitude 10. So step means 1 over s, but the magnitude of step is not 1, it is 10. So it's not a unit step input, it is a step input of magnitude 10. How to find the steady state error, E, of the closed loop system? If you're not sure, let's have a look at the list of equations down here. You look around and you notice this equation, first line, the last on your right. This is the equation that you use to find the steady state error because of the closed loop system, okay, EC. Okay, so EC of infinity or limit when time approaches infinity of EC of t equals to the limit when s approaches 0 of s ROS 1 plus g of s HOS. How we can put these brackets to make it clear. So now this is one important step to recognize which equation we need. Now we need to recognize or find out what these terms in this equation are. ROS is the input. So we're okay with that. GOS in this equation means the transfer function of the open loop system. HOS, just to clarify this, so we have G O of S and then we have H of S. So we know what we are talking about. Here we have R of S, and output you can call it any way you want, COS. But over here we said that H, assume H of S is 1. So we have a unity gain negative feedback loop. So this is 1. So now this steady state error is equal to limit S approaching 0 of what? S times 10 over S over 1 plus the open loop transfer function is our original transfer function, Ks plus 1 over S squared plus, sorry, X squared brackets S plus 2 brackets S plus 2. We know we are going to cancel S and S here. So when we do, we get 10 over 1 plus K 0 plus 1, 0 squared, 0 plus 2. 10 over 1 plus. Now, because of 0 here, this is going to be infinity. Infinity plus 1 is slightly more infinite. So it's still infinity. Anything divided by infinity is 0. So the steady state error is 0. Okay, case 2. Our input is now a unit ramp. So it's 1 over s squared. Sorry, EC, or infinity in this case, is limit s approaching 0 of s times 1 over s squared, 1 plus k s plus 1, s squared into s plus 2. Okay. Here we cancel s and 1 s here, so we have 1 over s. So 1 over 0 will give us infinity. Down here, we still have the same thing as before, 1 plus infinity, which is infinity. So this is a tricky situation because you get infinity over infinity, and you don't know what to do with that. I mean, maybe you think you know, but you are probably wrong. If you cancel infinity, infinity, and get 1, it may be true, but only if you are lucky. So let's do it properly, step by step. Limit s approaching 0 of 1 over s, and down here, it's s squared, s plus 2 plus k, s plus 1. And I'll bring this up here, times s squared times s plus 2. Now, canceling this s and this squared will give us s, which is 0, multiplying 0 plus 2. Down here we have 0. Let's squared, let's write everything here. 0 plus 2 plus k, 0 plus 1. Which will give us 0 in the numerator and k in the denominator. But this is still equal to 0. So in both cases, we have a 0 steady state error. And if you remember lecture 10, we had that table, we derived a table that no one expects you to remember, to memorize, okay? But in that table, we said the higher the type, the less the steady state error we are going to have. So we have a reasonably high type, type 2. So that's why we have 0 steady state errors. Okay, any questions so far? Part C, sketch the root locus. And as you can see, this part was the most important, at least last year. Sketch the root locus of this system. For your information, please don't tell anyone, root locus will be also the very important part of this exam, the most important part of my question. Actually, let's make a little digression here. In part A, in my part of the exam, which is worth 20 marks, the most important part will be root locus, then steady state errors as here, and there will be a very simple modeling question. And in my opinion, it will be a very simple modeling question. And it will be done such that a possible error in modeling that some of you may make, most of you won't, will not affect the rest of the question, how accurately you work on the question. So, if you're not happy, if modeling is not your thing, you can forsake those couple of marks, 3, 4, 8, 12, I don't remember anymore. Not that many. Root locus is the most important part. Drawing the root locus and analyzing root locus, that will be the most important part. But there will be a little bit of modeling. Again, I'll try to make it, no, I've done it. It will be a simple one. Okay, so let's sketch the root locus. Oh, sorry. Sorry? By what? Modeling. For example, the thing we started with. You get a system and you derive a transfer function of the system. Mathematical modeling of a system, yes?
So your part's 20 marks. How many marks is the
40. 20-20 split. You have that, you know, in course outline you have the values of each assessment. But what you don't have there is how much is for part A, how much for part B. So it's equal split. Okay, where are we? We've done with part B, steady state errors. Part C, sketch the root locus. So let's get the axis. Real part, sigma, imaginary part, j omega. No one expects you to know every rule by heart and really follow every rule exactly in the order they were presented in the lecture. We want you to draw a root locus. But let's try, at least without any notes, any reminder, try to think what were the basic rules. First of all, let's determine those points on the root locus where k equals to 0. Those points are the same points as poles of the open loop transfer function. So find these poles. There are 3 of them. 2 of them are at 0. So you have 2 poles coinciding here. And the third pole is -2. So you have 1 pole here at -2. Now, let's determine those points where the root locus finishes, where k equals infinity. Those points are the zeros of the open loop transfer function. So we have only one at s equal to -1. So here we have a 0. So 3 poles, 1, 0. So now you can already guess that because there are more poles than zeros by 2, that means that 2 of the branches of the root locus will end up at infinity. If you're not sure, wait until you apply other rules. So next important rule is to identify the segments of the real axis where the root locus exists. Where does it, first of all, how many segments do we have? 1, 2, 3, 4. Okay. The segment either completely belongs to the root locus or completely does not belong to the root locus. So there is no partial belonging. So this segment completely belongs to the root locus or doesn't? What do you say? It doesn't. Why? Because the number of singularities to the right of this segment is an even number, which is 0. So there are no poles, no zeros to the right of this huge segment. So there are no poles, no zeros to the right. There is no root locus on this part of the real axis. This segment here, does it contain or does it not contain the root locus? It doesn't, because there are 2 singularities on the right, which is, again, an even number. There are 2 poles, don't forget that. No root locus here. How about this one? Yes, because there are 3, 1 plus 2. So here we do have root locus. And this segment doesn't contain root locus because we have 1, 2, 3, 4. So there is no root locus to the left from -2. So only one part of root locus, only one part of the real axis, one segment of the real axis contains root locus. Okay, so now there are a few things we know. This is where k equals to 0. This is also where k equals to 0. This is where k equals to infinity. So root locus starts here at -2 and moves as k starts increasing from 0 to small positive numbers, then bigger and bigger. Where does this pole move? To the right. It has nowhere else to go but to the right, because this segment, once we determine this segment, we know that. On the other hand, this is where k equals infinity. So this is where the root locus finishes. Okay, it has nowhere else to come from apart from the left. So you can safely say that this pole will move towards this 0 as k becomes bigger and bigger. But what will happen with these two? They can't move left because there is no root locus on the left. They can't move right because there is no root locus from the right. So we guess they are going to move away from the real axis. That will be confirmed in a few minutes. Let's see about the asymptotes. How many asymptotes do we have? Number of asymptotes equals to the difference between the number of poles and number of zeros. 3 minus 1 is 2. If you're not sure about that, let's apply equations. So asymptotes are defined by the centroid, and centroid is the point of intersection between the asymptotes and the real axis, and the angles they create with the real axis, with the positive direction of the real axis. So once again, centroid is a point of intersection between the real axis and those asymptotes, no matter how many we have. That means that no matter how many asymptotes you have, 1, 2, or 10, they all intersect at the same point on the real axis. So that makes it easier. Once you find the centroid, that is valid for every asymptote you have. So let's apply this. Sigma A, sigma, which is the point where the asymptotes intersect the real axis, equals to the sum of minus pi minus sum of minus zi. So, and divided by the difference between number of poles and number of zeros. Now, we already said this is 2, 3 minus 1. But here, the poles are 0, 0, and minus 2. Minus, and now zeros are 1, minus 1 rather. Okay? So you have minus 2 plus 1, which is minus 1/2. So the centroid is here, sigma A, minus 1/2. This is where all asymptotes intersect the real axis. Now let's see how many asymptotes. Phi A By finding the angles, we also find how many asymptotes. Phi A, that's the angle between each asymptote and the real axis, positive direction of the real axis. So that is equal to 2q plus 1 over, again, np minus nz times 180. Yes? The value of the pole is minus 2. Oh, okay. No. Okay, very good point. Thank you. The transfer function, any transfer function, open loop, is a product of S minus Zi divided by the product of S minus Pi. That's right. Okay. So we should really rewrite this slightly better. 0 plus 0 and minus, but Pi has to be minus 2. What am I doing here? Right, okay. So all I can do now is have a quick look at my lecture notes, but I don't want you to think that's the way to solve this question in the exam. Okay, you're right. So this is, back to this. This should be plus. Is that what we said?
I don't know.
Okay, this is what we said. So it's minus 2 minus plus 1 over 2. No, that's even worse. Okay. Why? I mean, okay, so if the value of the pole is minus 2, the value of the 0 is minus 1. Yes? Okay, that's what you have in front of you. Okay, thanks. So I don't have to log on and everything. So this is plus, this is plus. Thank you. So now, P, we need a negative value of Pi, which is 0, 0, and minus 2. Okay, so for the third time. 0 plus 0 and minus 2. Thanks. Minus. Now, the value of Z is plus 1. So minus plus 1, okay, by 2. And that will give us, no, minus, but it's minus Z here, once again. Minus Z is here in the equation, so it is minus. Okay, so the transfer function has pluses everywhere. Pi is not the value of the pole, it's the value of the coefficient. Thank you, thanks. So we need a negative, here we want negative values of these coefficients. So if it is plus 2, we are putting minus 2 here. If this is plus 1, we are putting minus 1 here. So that will give us minus 1/2. Okay, so the equation seems right. At least no one complained last year. Maybe because they are not around anymore or whatever, I don't know. Okay, so it's minus 1. So definitely centroid is minus 1. Let's get the angles. Apart from we need to know what Q is. Well, Q is an integer. Integer, actually, this thing is NP minus NZ. Okay, so we start changing Q from 1, 2, 3 until these angles start repeating. So for Q equals to 1, it's 3 over 2, 3 halves. I don't know why I wrote this. I lost confidence now. Okay. 3 halves times 180, which is 270. That's for Q equal to 1. But it's easy if we start from 0. So if Q is 0, we have 1 by 2 times 180, which is 90 degrees for Q equal to 0. Now, if you say Q equals to 2, then you will have 5 over 2 times 180, which will be 450. But 450 is the same as 90. So there is no point going on anymore. You start getting the same asymptotes. So effectively, you have only 2. You have only 2 asymptotes, one at 90 degrees, which would be this one, and one as 270 degrees, which is this one. Oh, sorry. So now everything falls into place. You have 2 poles looking for a home, and then you have 2 asymptotes to take them home. Where is home? At infinity. So now it's all up to your sense of aesthetics, which is not something you're going to learn from me. But these 2 poles have to leave the real axis under 90 degrees. And then they have to somehow join these asymptotes and make sure there is a symmetry between the left and right half of your sketch. So this is your root locus. K approaching infinity, K approaching infinity. Okay, that's part C, root locus. Part D, let's get a little bit faster. Comment on the types of stability of the closed loop system that are achieved for different positive values of K. Make reference to values of damping ratio. So let's do that, part D. Okay, so let's have a closer look at this root locus. This pole always stays on the real axis and always stays on the left-hand side of the real axis. So this pole is always stable. So this pole doesn't worry us very much. It's these 2 guys. Initially, when K equals to 0, they are on the real axis, meaning non-oscillatory. Why do I say this pole doesn't bother us? First of all, it is always real. That means always exponential behavior, always non-oscillatory behavior. But second, because it is always on the left, it is also a stable pole. So the exponential is always like this, always decaying exponential, if you consider only this pole. But these 2, initially, they are both on the real axis, meaning non-oscillatory behavior. As soon as K becomes greater than 0, you get a pair of complex conjugate poles. So for K equal to 0, you have non-oscillatory behavior. For K greater than 0, damping ratio becomes less than 1, greater than 0. Which means that as soon as k becomes greater than 0, you have an oscillatory stable system. Why stable? Because these poles also move slightly to the left. As they move away from the real axis, they move to the left as well. Moving to the left means moving away from the boundary of stability, away from the imaginary axis. So we have stable, oscillatory stable. But let's have another look quickly what happens here. When k equals to 0, it is non-oscillatory, but is it stable? Or is it unstable? No, it's not stable, it's not unstable. It's neutrally stable because these poles are lying exactly on the imaginary axis. So neutrally stable. Okay. So this is a case when we actually don't significantly improve the behavior of this system with a negative feedback loop. No matter what value of k, well, we will stabilize the system, move away from the imaginary axis, but the cost is that we have oscillatory behavior. So we'll never have a non-oscillatory behavior of this system, unless k is 0. So that would be a kind of comment we expect. Okay? Any other questions? Or any questions? There are no questions. E, running out of time. Part E. What are the values of the poles if k is selected such that the system is neutrally stable? This is effectively a very simple question.